Hello, everybody, and welcome back to EarthSky. Scientists recently announced the intriguing discovery of a potential dark galaxy. And here to tell us what that is and what they found is David Lee, who led the study. Welcome, David.
Thank you.
It's
Happy to be
great to
here.
have you.
Happy to be here.
So before we get into what your team saw, just tell us, what is a dark galaxy?
A dark galaxy, well, basically, as the name suggests, is a galaxy that is very dark. So what that means is just they basically have very little stars. But then you will beg the question: how exactly does it make that a galaxy? Well, the main reason is that these galaxies are theorized to be pretty much completely made of the mysterious dark matter, which is basically the thing that makes up about 85% of the mass of the entire universe. That's probably one thing that we probably found.
So despite making up 85% of the universe's mass, as you say, dark matter is invisible, right? We can't directly detect it. So how do you detect a galaxy that is almost entirely dark matter?
So basically what we did was that we found these subclass of very faint galaxies, what we call ultra diffuse galaxies. So they're very, very faint, has very little stars. And we see that many of them actually have these things called globular clusters. So these are very bright, ancient, old star clusters that typically orbit around a galaxy. And so basically, we try to find these star galaxies or ultra diffuse galaxies by spotting these guys. So if we find clumps of groups of globular cluster that are seemingly orbiting nothing in the intergalactic space, then it probably indicates the location of a potential dark galaxy.
Right. So is there anything else that could be holding these, if you find these clusters in a group, is there anything else that could hold them together, or do you think that is a galaxy?
Yeah, that's a great question. So we primarily, the thing is, for globular clusters, they need a lot of gravity in order to hold them together, such as those from a galaxy. And typically, or at least statistically speaking, it is very unlikely for them to just clump together for no reason at all. Because typically what you would expect is just they will get, there was something called what we call a tidal debris. So these are basically just things that get thrown out from within a galaxy. But throughout that process, these globular clusters would typically just disperse away and would not just clump together. And so, but at the same time, for our discovery, these clumps of globular cluster, based on our statistical analysis, just the chance of them being coming from these tidal debris is just way too small. It's very, very, very unlikely.
Right. Okay. Yeah. And I think you said you found, was it 4 you found at first, the globular clusters? Right. Yeah. You find those and you see they're kind of centered around a point, and that's the point circled here, right? That is where the dark galaxy is.
Yeah, exactly.
And you might be thinking, I can't see anything, and I guess that is the point. How does this compare in terms of faint galaxies that we found?
For this guy, you mean like the brightness, right? In terms of comparison. Okay. So for this guy, I think in terms of the brightness or the surface brightness, what we call, so the average amount of light that this thing is emitting per unit area. This thing, I think, in the actual astronomical measurement, it's about 27 magnitude per arc second squared. So to give you a rough idea about how faint that is basically just above the sky noise background. So if you really try to find this thing using like a standard astronomical technique by pure imaging analysis, the chances are you would basically just take this as background noise. So you're not gonna pick it up. So in terms of comparing to other slightly brighter faint galaxies, I think, if I'm not mistaken, this thing is about like I don't want to throw out like random numbers, but based on what I remember, I think it's about 10 times fainter in terms of like the group of or population of faint galaxies that we know so far. So it is very faint.
Wow. Yeah. That is amazing.
Yeah.
And obviously that's because it is so heavily made up of dark matter. You say in the paper that it's up to 99.99% of this galaxy's mass could be dark matter.
Yeah.
And also that up to 33% of its visible light could be from these star clusters.
Yeah.
How does that compare to the Milky Way or a typical galaxy?
So yeah, that's a pretty massive differences compared to the Milky Way. So in terms of the global cluster, the light coming from the global clusters compared to the Milky Way. So Milky Way only has about 0.1% ish of its light coming from its global clusters. So majority of the light from the Milky Way comes out, as you can see in the image over here, are from what we call the field stars. So these are, for example, like the sun is a field star. So it's not living inside like a dense star cluster. So it's basically out there in the field, in the empty space. And so, yeah, for a Milky Way and a standard typical galaxy, this global cluster mass ratio or light ratio is actually incredibly low. And in terms of the dark matter content for Milky Way, I think there are a lot of different estimates so far based on different research groups. But I think the primary estimates right now, it's about 90%-ish. So it's still pretty high, but not as high as 99.99%. So
right. Okay.
But yeah, I do have to note though, like the figures that we quoted in the paper, that actually it was based on a lot of assumptions, but those assumptions are basically based on established astronomical previous observations about other galaxies, what they typically behave. So that's as I said, this is basically kind of a extrapolation at this point.
Yeah.
Yeah.
Right. But either way, it's not in the same ballpark as any galaxies we think of when we think of normal galaxy. So what has caused this galaxy to have such a crazy proportion of dark matter compared to the Milky Way, for instance?
So basically the current leading theory about this is actually there have been a couple of other really faint or ultra diffuse galaxies that we have found that is actually very similar to this guy or CDG2. Right? So the current theory is that these galaxies are basically formed in like a massive dark matter halo, but because the positions that they're in, so these guys are typically formed inside like a really dense, massive galaxy cluster environment. So the gas and dust that you need to produce new stars from these guys, they basically get stripped away. Because they're in these really dense and chaotic, violent environment. But the thing is, the dark matter was still there. Right. So what happened was that the only stars that got formed or that got produced are basically the stars within the global clusters. And then that's it. You don't form stars anymore. But the thing is that because the dark matter halo is still there, so they still keeping those global clusters together. And that's how we are able to see them.
Right, because globular clusters tend to be kind of the earliest parts of a galaxy formation, right? They're kind of the most ancient stars we find.
They're one of the oldest star population that we know of as of today. Yeah.
So it got going, but then it just couldn't keep it up in the end, and it just
it doesn't in the field, like in the empty space, they don't have enough like gas for like sun like stars like our sun to form in a loose kind of manner. Yeah.
Does that mean it's likely that there would be other similar galaxies nearby, like within that same dark matter halo?
We don't know. Actually, the thing is, we did find another one. This is why this galaxy called CDG2, because we previously found CDG1, which is also another clump of 4 global clusters. But the thing is, we cannot confirm its like nature because we don't see any like faint glow of light that surround the 4 global clusters. The main reason we can confirm the nature of this one is because we actually found very, very faint, like diffuse light surrounding the 4 global clusters, as you can see. I mean, it's still very hard for you to see in this picture, but the thing is, like, when I tell you there's something there, you're like, I think I see it.
Yeah, you can just about see it, for sure.
Yeah, you just about see it. But for the CDG1, there's nothing there. Absolutely
nothing there at all.
Yeah.
Right. That's a good point. CDG stands for candidate dark matter candidate dark galaxy, right? So this is a candidate. Is there something that could provide even stronger evidence that that is what this is? What's next for the study?
Yeah, so the next thing I think we've hinted in the paper multiple points is that we need like much better and deeper observation of this thing. So basically, the primary thing that we need is to see whether there are fainter global clusters that we don't see in this galaxy. And the second thing is we probably want to get like what we call spectroscopy data for the global clusters, so we can measure, for example, their their velocity or kinematic data. So basically measure their velocity and actually try to confirm that based on their kinematic data, we can basically infer exactly how much mass there is in CDG2. So then we could determine exactly how much dark matter there is in this galaxy.
Right, and that's not next generation telescope stuff. That is doable now, is it?
Yeah, I think we probably need to do a little bit of calculation to see how powerful of a telescope that we need in order to do that, because we haven't done that yet. But the thing is, we probably do need something like JWST, so James Webb, to actually do that, because this thing is really far away. It's like 250 million light years away ish. So it's not an easy thing to do. So
yeah, it's like a 90% invisible, and it's 250 million light years away.
Yeah, exactly.
You need a big telescope.
Yeah, you need really, really powerful telescope to do that.
Right. Well, fantastic. We'll be watching for any further developments if you can get that time. And this has been fantastic, David. Thank you very much.
Yeah, thank you very
much for joining us. And thanks for watching, everyone. We are here every weekday at 12:15 Central Time, bringing you the latest scientific discoveries straight from the experts. So until next time, one Earth, one sky, EarthSky.